Good afternoon, folks. How are you today? In the past few weeks, we have learned how to solve one nonlinear equation in one unknown. Now we are going to learn how to solve n linear equations in n unknowns. But before we go on to n linear equation, let's look at one linear equation. So we have one linear equation in one unknown, and we write it like this. So we know A, we know B, we want to find X. That's our unknown. So let's look at several of the possibilities. If A is 0 and B is 0, then X can be anything. So that means we have no unique solution. So if A is 0 and B is 0, we have no unique solution. Now let's look at second situation. A is 0 and B is not 0. So if A is 0 and B is not 0, then of course X cannot be finite. So we say we have no finite solution. Okay, so we have no finite. So these two cases are not very interesting. Let's consider the third case. A is not 0 and B is 0. Well, if A is not 0, B is 0, X must be 0. So X is equal to 0 is a trivial solution. And finally, we have the last case. A is not 0 and B is not 0. In that case, we know that X would be B divided by A, and we will have a unique solution because both B and A are finite. And this is the solution we are most interested in. A unique solution. So now when we have many equations, linear equations in many unknowns. So let's say we have m equations in n unknowns. We will write them in this compact form A times X is equal to B, where A, X, and B are matrices. So we want to learn more about matrices. So here is what will happen over the next couple of weeks. I'm going to introduce you to matrix algebra, which is linear algebra. And then we are going to learn about uniqueness of a solution. I showed you a very simple example. When we have one equation, one unknown, we'll talk about conditioning of a system. And then we will learn methods to solve this linear system. We will learn direct methods. We will learn iterative methods. And then we'll look at some applications. Before I move on, of course, some of you have already taken a linear algebra course. So what you may find over the next 2 weeks is a very practical application of what you have learned. And I hope maybe this repetition would clarify things for you. For those of you who have not taken a linear algebra course as yet, you are not at any particular disadvantage compared to people who have taken linear algebra. I hope my introduction will help you when you take your linear algebra course. So let's begin by talking what is really a matrix. So matrix is really a collection of things that are arranged in a tabular form. So if we arrange things in a tabular form made up of rows and columns, we call it a matrix. So this matrix we call A, and it has 2 rows and 3 columns. So we always show the size using subscript. First is always number of rows followed by number of columns. And then we can identify each element of the matrix by its row and column number. So this is first row, first column. This is second row, second column, and so on and so forth. So a matrix A m by n is a collection of elements Aij. So this represents the size, and these are the row column numbers of the elements. And here, of course, number of rows go from 1 through m, and number of columns go from 1 through n. So what we are going to do is we are going to keep a kind of a tree on a different page, and I'm going to come to this page over and over again. So if you're taking notes, you might. So we have general case, a rectangular matrix. And it has a very special case known as vectors. So vectors are basically one-dimensional matrices. So if it is one-dimensional, it can be horizontal, in which case we call it a row vector. So a row vector has one row and can have many columns, as many as we want. Another special case is a column vector. So column vector, as the name implies, has one column. So we'll call it X, and it has m rows and one column. Another special case of a rectangular matrix is a square matrix. Square matrix, as the name implies, has same number of rows and columns. So I'm going to come to that page in a moment. So here is our square matrix, A n by n. So let's say in this case we have 3 rows and 3 columns. So what we do is we define elements on this diagonal, and we call this diagonal as principal diagonal. So our principal diagonal always goes from top left to bottom right. So of course these diagonal elements, you can see this is first row, first column, second row, second column, third row, third column. So these elements are always having subscripts II, same subscript. So now we go back and we are going to talk about special cases of a square matrix. So special cases of a square matrix are called triangular matrices. And there are two kinds. One is called lower or left triangular, and other called upper or right triangular. So typically we use L and U for it. Remember, they are all special case of square matrices. So what we do is we say lower is, if we look at the principal diagonal, all elements above the diagonal are 0. So that's our matrix. So notice, if I take any element here, this is L11, this is L12, L13. Whenever the column number is larger or row number is lower than the column number, then that element has a value of 0. Let's see the other kind. In the other kind, if this is our principal diagonal, all elements below are 0. So you can see here, whenever row number is greater than column number, so this is U31, U32, so on and so forth, then that element is 0. Okay, so let's take a special case of these triangular matrices and build our table again. So a special case of these triangular matrices is a diagonal matrix. So we'll call it dn by n. And a little later we'll find out a special case of this is a scalar matrix. I'm going to go over this in a moment. Just want to show you the tree. And a special case of a scalar matrix is an identity matrix or a unit matrix. So let's go back to our examples. So what is a diagonal matrix? This is our principal diagonal. All elements above and below are 0. So we say whenever row number is not same as column number, the elements are 0. Then a special case of diagonal matrix is a scalar matrix. In a scalar matrix, not only all the off diagonal elements are 0, but the diagonal elements are all alpha. So we say SII is equal to alpha. So alpha can be any value. And a special case of a scalar matrix is identity or unit matrix. This is a very important matrix. And here what we have is, since it's a special case of a scalar matrix, all the alphas are equal to 1. So we say I is equal to 1. So this is our different types of matrices. Now let's look at operations. So what kind of operations can we perform? We can perform arithmetic operations. We can perform geometric operations. We can perform logical operations, and we'll see each of these. So let's begin by talking about arithmetic operations. So arithmetic operations we do are add, subtract. Well, these are essentially identical things. So whenever we are saying add or subtract, we can say add a negative of that matrix. Then we have multiply, and finally we have divide. So we'll find out most of the linear system is about this idea of implementing something which is analog to division. But let's say, suppose we have two matrices and we want to add or subtract one from other. In order for us to do that, they must be same size. So they can be rectangular, but they must be of same size. That's the key idea. And of course, the result would be of the same size as well. So it is very, very simple. Suppose we have a matrix 1, 2, 3, 4, 5, 6, and we add, let's say 7, 8, 9, 10, 11, 12. So our result would be, of course, same size, 2 rows, 3 columns. So we just add element by element. 1 plus 7 is 8, 2 and 8 is 10, 9 and 3 is 12, 14, 16, and 18. So we say Cij is Aij plus or minus Bij. So that's element by element, addition or subtraction gives us the result. Now let's look at multiplication. So there are two kinds of multiplication. One called scalar multiplication. One is our matrix multiplication. So what's our scalar multiplication? Suppose we have a matrix m by n. We multiply it by some scalar alpha, and our result would be b m by n, same size matrix. So it's very simple, probably intuitive. Bij is alpha times Aij. We just take each element of A and multiply it by alpha and gives us the result. So if A is 1, 2, 3, 4, 5, 6, and we multiply it by 5, which is our alpha, our result is going to be 5, 10, 15. We are just multiplying each element by 5, 20, 25, 30. Okay. So different example, but you get the idea. Now, the most involved operation of the three is matrix multiplication. So here, if we have A and we want to multiply it by B, B must be conformable to A for multiplication. What does that mean? If A is M by P, it has P number of columns, then B must have same number of rows. And so this must be same. And then our result is C, which is M by N. So what we do is, suppose we have A and we have B, they need not be of the same size. Remember, Number of columns of A must conform to number of rows in B. So what we do is we pair them up. So we take this entire row and multiply it by this column like a dot product, and that gives us our result for this. So if we want C11, we take first row of A, multiply it by first row of B. If we want C12, we take first row of A, multiply it by second row of B, and form pairs. So let's see an example. So let's say A is 1, 2, 3, 4, 5, 6. And B is, so remember, A has 2 rows, 3 columns. So B must have 3 rows at least. So we'll put 3 rows. It can have any number of columns to keep it simple. Let's put just one more column. So our result C would be, so this is same. So C would be 2 by 2. So let's write C. So this C11 will pair up 1, 2, 3 with 7, 8, 9. So we'll say 1 times 7 plus 2 times 8 plus 3 times 9 will give us 50. So you can see I've given the details here. So we are interested in C12. We'll take first row, second column, pair them all up, and then add them. Second row, first column, we'll take second row times first column, pair, add them up. Second row, second column, second row, second column, pair them up, and you'll get minus 17. So if we have a system of equations, a n by n times x n by 1 is b n by 1, which is a linear system. We know a, we know b, we want to find x. So you might say, well, let's take b and divide it by a. But this division is not defined. So we need to simulate it. And that's what linear algebra or linear systems are all about. So what we do is, since we can't just divide, what we do is, in principle, we think about multiplication. So we say we are going to take 1 over a and multiply it by b. And this 1 over a is called A inverse or matrix inverse. So we can do matrix multiplication. This is allowed. So what we'll do is we'll somehow find out what is 1 over a. So if A inverse exists, it is only for square matrices, then we can perform this multiplication and solve for x. So we'll talk about this later on. Let's look at logical operations. So what are our logical operations? We call them relational operations. And they are greater than, less than, equal to, not equal to, things like that. So if we have two matrices, we cannot compare. So we can't say one is bigger than the other. We can only test for equality. So we can't only say if two matrices are equal and or not equal. So if we need to test for equality, first of all, they must be of the same size. Secondly, element by element, the two matrices must be identical. So we say for all row and column combinations. So this inverted A means for all. And no other relational comparisons are defined. Okay, let's see our last operation, which is geometric operations. So one of this is called matrix transpose. So suppose we have a matrix A m by n. So what we do is we take its transpose. So when we take its transpose, we get a matrix B, which is n by m. So whatever were the rows of A, we make them columns of B. Whatever were columns of A, we make them rows of B. So what we are saying therefore is Bji is equal to Aij for all ij combinations. So let's see, suppose we have a matrix 1, 2, 3, 4, 5, 6. So this is our matrix A, 2 rows, 3 columns. So when we take its transpose, we'll get a result. Our result would be B, which is going to have 3 rows now and 2 columns. So first row will become first column, second row will become second column. So you can see first column is first row, second column is second row, third column is third row. Based on this, we can talk about some properties about symmetry. So when we talk about symmetry, we can only talk about square matrices. So if we have a matrix A n by n, and if this matrix is symmetric, remember square matrix, it has a principal diagonal. We say matrix is symmetric if elements on the opposite sides are equal. So what we mean is if Aj is equal to Aij. So let's look at our example. So here is a 3 by 3 matrix. So you can see 7 and 7 identical, 9 and 9 identical, 3 and 3 identical. So A is symmetric. Let's look at matrix B. 7 and 2 not equal. So right away fails. B is not symmetric. Another kind of matrix is called skew symmetric. In skew symmetric, the off diagonal element are opposite, same magnitude, but opposite in sign to one another. So we have Aj is equal to minus Aij. So as soon as we say that, what happens when j is equal to I? If j is equal to I, the diagonal element would be equal to the negative of itself. So that would imply, therefore, that Aii must be 0. All the diagonal elements must be 0. So let's look here. Matrix A, diagonal elements are all 0. 7, negative 7. 9, negative 9. Negative 3, positive 3. So this is skew symmetric. Here, the diagonal elements are not 0. So right away, not skew symmetric. But let's suppose if the diagonal elements were 0, then 7, negative 7, it'll become same as this matrix A effectively, right? Hey, last of our property. The last of our property is called matrix determinant. And we can find determinant only for square matrices. It turns out the definition of determinant is recursive. So I'm not going to write this down because it is written much nicely here. Basically, determinant of a square matrix is a sum of many terms. Each term alternates with a sign, and then we have the element of the matrix times the minor of that element. So what is a minor? Minor itself is the determinant of the smaller matrix when we remove row I and column j. So this becomes kind of a recursive definition because to define determinants, I'm using the word minor, but then minor itself is determinant of some other matrix. But let's start with 1 by 1 matrix. So suppose we have a 1 by 1 matrix. So this determinant of this 1 by 1 matrix is the element itself. And then we build upon it. So if we have a 2 by 2 matrix, we want to find its determinant. We multiply this times this, and we subtract this times this. Now, there are similar definitions. I'm sure you may have learned it in some earlier course. Determinant of a 3 by 3 matrix, which we can do by hand. But once we go more than 3 by 3, you really need a calculator or a computer. But based on this property, we say if determinant of a matrix A is not 0, then we say a inverse exists. So inverse is like 1 over A. So remember, if we can find 1 over A, then we can implement kind of matrix division. So what are the properties of this A inverse? If we take A and multiply it by A inverse, post multiply, we'll get matrix I, identity matrix. It doesn't matter whether we post multiply or pre multiply. Both is results in same I matrix. So as written here, other than paper pencil calculations, 2 by 2, 3 by 3 is okay. After that, finding determinant and inverse using these definitions, these mathematical definitions, is not very efficient. Now it turns out Excel, as you can see right away, Excel is basically a big, huge table. Each worksheet is a big, huge table. So it's perfect for doing matrix calculations. The only thing is, when we talk about a matrix consists of multiple cells. So whenever we need to compute multiple cells simultaneously, we need to press, usually whenever we are dealing with one cell, we press enter. Now once we select multiple cell, we'll have to hold down control, hold down shift, and then press enter. Since we'll be dealing with lots of cells, it's a good idea to name matrices. So the key things are, typically plus minus is algebraic. If we want to do matrix multiplication, there is a special function in Excel called mmult. So mmult multiplies P by Q. There is also a dot product function, which is called sum product. So you have learned in your statics course, dot product of two vectors, P dot Q. So there is an Excel function for that. We just learned about transpose. There is an Excel function for that. We are going to learn much more about inverse in our next lecture, but there is an inverse function. And then finally, we just talked about determinant, a matrix determinant. There is a matrix determinant function which finds determinant of A.